In the depths of the universe, where light can no longer reach, there are phenomena unseen, yet powerful enough to change everything. Welcome. You are now on Boring Sleep, a place where we don't rush, we don't raise our voices, and we don't chase excitement. Here, we create slow documentaries with calm narration, designed to help you relax and fall into deep sleep. If you enjoy this kind of content, you may subscribe to the channel quietly. In this documentary, we will take you on a very distant journey into the depths of the universe, where invisible objects exist, yet their gravity changes everything. Tonight, we will talk about black holes. What are they? How do they form? And what would happen if we came too close? This documentary is long, slow, and carefully designed for sleep. You may close your eyes now and let the sound guide you. Before we begin to understand what a black hole truly is, it is important to slow down, to step away from images, from movies, and from dramatic ideas, because the universe does not rush, and neither should we. In the vast silence of space, far beyond the limits of human senses, there are regions that do not shine, do not reflect light, and do not announce themselves. They exist quietly, yet their influence is profound. A black hole is not a hole in the common sense of the word. It is not an opening, and it is not empty space. It is a region of the universe where gravity has become so strong that the familiar behavior of matter, light, and even time begins to change. We cannot see a black hole directly. It produces no light of its own. It reveals itself only through what surrounds it, through stars that move strangely, through clouds of gas that spiral inward, slowly heating up before fading into darkness. To understand how a black hole exists, we must first understand gravity. Gravity is not simply a force pulling objects together. It is the curvature of space and time itself. Every object with mass bends the universe around it. The planet bends space gently. A star bends it more deeply. A black hole bends it completely. When a massive star is born, it begins a long and stable life. For millions of years, sometimes billions, energy produced in its core pushes outward, balancing the inward pull of gravity. This balance keeps the star alive. Eventually, the fuel runs out. The outward pressure weakens. Gravity no longer has an equal opponent, and the star begins to collapse. For smaller stars, this collapse ends quietly. But for the most massive stars, there is no force strong enough to stop the inward fall. Matter is compressed further and further until space itself gives way. At this moment, a black hole forms, not with sound, not with intention, but as a natural consequence of gravity reaching its limit. Around every black hole exists a boundary that is not solid, not visible, and not physical. This boundary is known as the event horizon. The event horizon marks a point of no return. Once crossed, nothing can escape. Not matter, not energy, not even light. From a distance, an object falling toward a black hole appears to slow down. Its movement stretches. Its light becomes dimmer, redder, until it fades completely. To the falling object itself, nothing feels sudden. Time continues normally. There is no line in space, no moment of realization, just a quiet continuation forward. Black holes exist in many sizes. Some are only a few times the mass of our sun. Others are enormous, millions, even billions of times more massive than the sun. These supermassive black holes sit calmly at the centers of galaxies. They do not consume constantly. They do not wander. They remain anchored. At the center of our own galaxy, there is such a black hole. It does not threaten Earth. It does not pull us inward. It simply exists, shaping the motion of stars over time. Contrary to popular belief, black holes are not cosmic destroyers. They do not pull everything toward them. Their gravity follows the same rules as any other object with mass. If our sun were replaced by a black hole of equal mass, the planets would continue their orbits unchanged. What lies at the center of a black hole remains unknown. A region called the singularity, the place where density becomes infinite and our equations fail. This is not a failure of nature. It is a limit of human understanding. Black holes are not violent by nature. They are patient. They evolve slowly. They shape galaxies over billions of years. They remind us that the universe is not dramatic. It is subtle. It is consistent. And it is vast beyond imagination. In learning what a black hole is, we are not learning about destruction. We are learning about structure, about balance, and about the quiet rules that govern everything that exists. And this understanding has only just begun. As we continue deeper into the nature of black holes, our focus moves closer, not to the center, but to the boundary. This boundary is not something you can touch. It has no surface, no texture, no color. Yet it defines everything that follows. This boundary is known as the event horizon. The event horizon is not a wall. It does not stop objects suddenly. It does not flash or glow. It is simply a point in space where escape becomes impossible. Far away from a black hole, space behaves normally. Light travels freely. Time moves at a familiar pace. Gravity feels predictable. But as an object slowly approaches the region near the event horizon, the rules begin to shift. Gravity grows stronger, not abruptly, but gradually. Time itself begins to slow, not for the object falling inward, but for those watching from afar. To a distant observer, the falling object appears to move more slowly. Each second stretches longer than the last. Motion becomes gentle, almost frozen. Light leaving the object must climb out of an increasingly deep gravitational well. As it does, the light loses energy. Its color changes. It becomes redder and dimmer. Eventually, the light fades beyond detection. The object does not disappear suddenly. It simply becomes unreachable. For the object itself, the experience is different. Time continues normally. The laws of physics still apply locally. There is no sudden alarm, no visible boundary in space. Crossing the event horizon does not feel like crossing anything at all. This difference in experience is one of the most important lessons black holes teach us. Time is not universal. It depends on gravity. It depends on motion. It depends on where you are. Near a black hole, time slows dramatically. Clocks tick more slowly. Processes take longer. From the outside, time near the event horizon appears almost stopped. This effect is known as time dilation. It is not science fiction. It is a measurable consequence of gravity itself. The stronger the gravity, the slower time moves. And near a black hole, gravity becomes extreme. Space itself is also affected. Distances stretch. Paths curve. Straight lines bend into arcs. Light passing near a black hole does not travel in a straight path. It curves around the mass. Stars behind the black hole appear distorted, stretched, duplicated. This phenomenon is known as gravitational lensing. It allows scientists to detect black holes indirectly by observing how light behaves in their presence. The event horizon is not a place of chaos. It is calm, silent, mathematically precise. Nothing special happens at the horizon itself. No sudden tearing of matter. No violent forces acting instantly. The true extremes lie deeper, beyond what we can observe. Yet even without crossing it, the event horizon defines the character of a black hole. It separates the known from the unknowable. For scientists, this boundary represents a challenge. Our theories describe space and time well until they reach this edge. Beyond the event horizon, information cannot return. Signals cannot escape. Causality itself becomes unclear. This raises deep questions. What happens to information? Is it destroyed? Or is it preserved in some unknown form? These questions remain unanswered. They are not solved yet. They may require new physics. Despite these mysteries, the event horizon remains peaceful. It does not radiate danger outward. It does not announce itself. It simply exists, marking the limit of what the universe allows us to see. In the quiet study of this boundary, we learn something unexpected. The universe is not hostile. It is indifferent. It follows rules with patience. And black holes, through their event horizons, show us that reality is deeper than appearance, slower than expectation, and far more subtle than intuition suggests. Beyond the event horizon, there is no return. Not because of walls or barriers or forceful resistance, but because the structure of space itself no longer allows escape. Everything that crosses this boundary continues inward, not pulled violently, but guided by geometry. Inside a black hole, all possible paths lead in the same direction, forward, deeper. This is difficult to imagine because human experience is built on choices of direction, left or right, up or down, forward or back. Inside a black hole, direction loses its meaning. There is only one future. At the heart of this inward journey lies a concept known as the singularity. The singularity is not a place in the usual sense. It is a point where matter is compressed beyond all known limits. Density becomes infinite. Volume shrinks to 0. At this point, our equations stop working. The laws of physics as we currently understand them fall silent. This silence does not mean destruction. It means uncertainty. It marks the boundary between what we know and what we have yet to understand. Scientists do not claim to know what truly exists at the singularity. Some theories suggest that matter continues to collapse endlessly. Others propose that new physics intervenes. Quantum effects, normally insignificant at large scales, may become dominant here. Gravity, described by general relativity, and quantum mechanics, which governs the smallest particles, do not yet agree in these extreme conditions. This disagreement is one of the greatest challenges in modern physics. Black holes force these two theories to confront one another. They reveal the limits of our current understanding. Yet even in this uncertainty, black holes remain calm. They do not destabilize the universe. They do not unravel reality. From the outside, a black hole appears simple, defined by mass, by spin, by electric charge. Everything else is hidden. This idea is known as the no-hair theorem. It suggests that black holes lose all detailed information about the matter that formed them. Whether this information is truly lost or merely hidden is still debated. This question leads to the information paradox. If information is destroyed, it challenges fundamental principles of physics. If it is preserved, we do not yet know how. Some theories propose that information is encoded on the event horizon itself. Others suggest that it escapes slowly through subtle quantum processes. One such process is known as Hawking radiation. Over extremely long timescales, black holes may lose mass. Not suddenly, not dramatically, but slowly, quietly, over trillions of years. This idea transforms black holes from eternal prisons into temporary structures on cosmic timescales. Even this evaporation is gentle, invisible to human senses, relevant only to the far future of the universe. Black holes are often described as extreme, but extreme does not mean violent. They are governed by precise mathematics. They obey strict rules. They evolve predictably. They exist not as chaos, but as order pushed to its limits. In studying black holes, humans confront something profound. Not danger, but humility. We learn that the universe does not reveal all its secrets at once. Some truths require patience. Some require new ways of thinking. And some remain beyond reach, waiting silently at the edge of knowledge. Black holes do not answer every question. They teach us how much remains unknown. They remind us that mystery is not failure. It is invitation. An invitation to observe more carefully, to think more slowly, and to accept that not everything must be understood to be appreciated. In their quiet persistence, black holes hold a mirror to the universe itself. Vast, patient, unrushed. And as we pause here, at the edge of what can be known, we prepare to continue, not inward, but outward, toward the role black holes play in shaping galaxies, stars, and the structure of the cosmos. Long before black holes became objects of study, before equations, before telescopes, they existed quietly as natural outcomes of the universe itself. To understand how black holes form, we must return to the earliest moments of cosmic history. The universe began in a state of extreme simplicity, hot, dense, uniform. As it expanded and cooled, matter began to gather. Tiny irregularities grew over time. Gravity amplified small differences. From these subtle variations, the first stars were born. These early stars were unlike the stars we see today. They were massive, short-lived, composed almost entirely of hydrogen and helium. Without heavier elements, they burned their fuel rapidly. Their lives were brief, but intense. When these massive stars reached the end of their short existence, gravity again became dominant. Some exploded outward, spreading elements into space. Others collapsed inward, creating the first black holes. These earliest black holes were not isolated events. They became seeds. Over time, they attracted surrounding matter. Gas clouds drifted inward. Stars formed nearby. Galaxies began to take shape. Black holes did not create galaxies alone, but they influenced their structure. They shaped their growth. They regulated their evolution. As galaxies merged, their central black holes merged as well, slowly increasing in mass, quietly growing. Across billions of years, small black holes became larger ones. Larger ones became supermassive. Today, almost every large galaxy contains a supermassive black hole at its center. These black holes are ancient, older than most stars, older than planets. They do not dominate by force, they dominate by presence. The formation of a black hole does not always require violence. Some stars collapse directly, without explosion, without outward display. This process is known as direct collapse. In these cases, a black hole forms silently. No light announces its birth. No shock wave travels outward. The universe continues, unaware. Black holes can also form in environments where stars are crowded, dense clusters, galactic cores. In such regions, stars interact frequently. Mass transfers occur. Collisions become possible. Under these conditions, black hole formation becomes more likely. Yet not every star will become a black hole. Most end their lives as white dwarfs or neutron stars. Only the most massive cross the threshold where gravity overwhelms all resistance. This threshold is precise. It depends on mass, on composition, on rotation. When crossed, there is no reversal. Black holes form not as anomalies, but as natural endpoints in the life cycle of stars. They are not mistakes. They are outcomes. In the broader picture of the universe, black holes are neither rare nor dominant. They are balanced. They appear where conditions allow. They grow where material is available. They remain where gravity holds them. The universe does not rush their creation. It allows it to unfold over immense timescales. In this slow unfolding, black holes become part of the cosmic rhythm. They are born, they grow, and eventually they fade. Their formation marks not an end, but a transformation. Matter becomes curvature. Energy becomes geometry. Stars become silence. And from this silence, structure emerges. Understanding the birth of black holes is not about catastrophe. It is about continuity. about how the universe reuses its material, about how gravity shapes complexity from simplicity. As we pause here at the beginning of this story, we prepare to explore further how black holes grow, how they interact with their surroundings, and how they influence the vast architecture of the cosmos. After their formation, black holes do not remain unchanged. They grow slowly, quietly, over vast stretches of time. Growth does not happen all at once. It depends on environment, on availability, on chance encounters within the universe. A black hole grows by absorbing matter, gas, dust, occasionally entire stars. This process is not violent by default. Most matter does not fall straight in. Instead, it begins to orbit. As gas approaches a black hole, it forms a rotating structure known as an accretion disk. Within this disk, matter spirals inward gradually. Friction builds, temperature rises, energy is released. Ironically, some of the brightest objects in the universe exist because of black holes. The light does not come from the black hole itself, but from the heated material just before it disappears. In some cases, this energy becomes powerful enough to push matter outward. Jets of particles are launched into space. These jets travel vast distances. They shape galaxies. They heat surrounding gas. They limit star formation. Through this balance of feeding and release, black holes influence their environment deeply. They do not merely consume, they regulate. In young galaxies, rapid black hole growth can slow the birth of new stars. Gas that would form stars is instead heated or expelled. In older galaxies, black holes settle into a quieter role. Occasional feeding, long periods of calm. This rhythm of activity and rest continues for billions of years. When galaxies collide, their black holes begin a slow approach. They orbit each other over immense timescales. Energy is lost. Distance decreases. Eventually, they merge. This merger releases ripples in space itself. Gravitational waves spread outward, passing silently through the universe. These waves carry information about mass, about motion, about cosmic history. In recent years, humans have learned to detect them, not with light, but with motion. Tiny vibrations in space-time itself reveal these distant events. Through these observations, black holes become measurable. Their growth becomes traceable. Yet, despite this progress, most black holes remain unseen, inactive, quiet, dormant. They drift through time without announcement. Even the supermassive black hole at the center of our galaxy is calm. It feeds slowly. It emits little energy. Life on Earth is unaffected by its presence. Black holes do not seek dominance. They respond to opportunity. Where matter gathers, they grow. Where it does not, they wait. This waiting can last longer than civilizations, longer than species, longer than memory. In this sense, black holes represent patience on a cosmic scale. Their growth is not a race. It is an accumulation, a gradual reshaping of mass into gravity. Understanding this process helps scientists explain why galaxies look the way they do, why stars form where they do, why some regions remain quiet. Black holes are not isolated entities. They are participants in a larger system. They listen to the universe around them. They respond to its structure. Through growth and interaction, black holes become architects of cosmic order. They shape without intention. They influence without awareness. They exist without urgency. And as they continue their slow evolution, they remind us that even the most extreme objects can act with restraint. Growth in the universe does not require noise. It requires time. As black holes continue to grow and interact with their surroundings, their influence extends far beyond their immediate vicinity. They do not remain isolated points of gravity. They become part of a much larger system. This system is the galaxy. Galaxies are not static structures. They are dynamic. They breathe. They evolve over billions of years. Within this slow evolution, black holes play a subtle but essential role. At the center of many galaxies, supermassive black holes reside quietly. They do not dominate by constant activity. Most of the time, they are inactive, silent. Yet even in silence, their presence matters. Gas within a galaxy moves. It flows inward. It cools. It collapses. From this process, new stars are born. But this process cannot continue unchecked. If star formation were unlimited, galaxies would burn through their material too quickly. They would exhaust themselves. Black holes help prevent this. When a central black hole becomes active, it releases energy into its surroundings. Not continuously, but in episodes. These episodes heat the surrounding gas. They slow its collapse. They regulate the pace of star formation. This balance is known as feedback. Feedback is not destruction. It is regulation. Without feedback, galaxies would grow too fast. With too much feedback, they would stop growing entirely. Black holes help maintain this balance. In massive galaxies, this regulation is especially important. Their large gas reserves require careful control. Observations show that galaxies with larger central black holes often form fewer new stars. Their growth becomes calmer, more stable. In smaller galaxies, black holes play a gentler role. Their influence is present, but limited. This difference shapes the diversity of galaxies we observe today. Across the universe, galaxies collide and merge. These encounters are slow. They unfold over hundreds of millions of years. When galaxies merge, their stars pass mostly unharmed. The vast distances between stars prevent frequent collisions. Their gas clouds, however, interact strongly. They compress. They ignite bursts of star formation. At the same time, their central black holes begin a long dance. They spiral inward, losing energy gradually, until they merge. This merger reshapes the galaxy. Its structure changes. Its star formation slows. Its future is altered. Through these processes, black holes influence the large-scale architecture of the universe. They help determine which galaxies remain active and which become quiet. They influence the distribution of matter, the flow of energy, the balance between growth and stability. This influence is not intentional. Black holes do not decide. They respond. They respond to gravity, to motion, to the availability of matter. In this way, they act as stabilizing agents, not rulers, not destroyers, but regulators. On the largest scales, the universe itself is shaped by gravity. Black holes represent gravity in its most concentrated form. By studying how they affect galaxies, scientists gain insight into the evolution of the cosmos. They learn why galaxies have the sizes they do, why star formation slows with age, why the universe today looks different from the universe of the past. These answers do not come quickly. They require patience, long observation, careful measurement. Black holes teach us that influence does not require constant action. Sometimes, presence alone is enough. In their quiet persistence, black holes help maintain the long-term stability of cosmic structures. They allow galaxies to mature, to settle, to age gracefully. Without them, the universe would look very different, less ordered, more chaotic. Yet despite this importance, black holes remain mostly invisible. Their work is subtle, their effects indirect. They shape the universe without demanding attention. As we observe the night sky, we see stars, nebulae, galaxies. Behind this visible beauty, black holes operate quietly. They remind us that not all power is loud, not all influence is obvious. Some of the most important forces in the universe work in silence, over time, guided only by the steady rules of gravity itself. Black holes do not reveal themselves easily. They emit no light. They reflect nothing. They remain hidden against the dark background of the universe. For a long time, this made them objects of theory, not observation. They existed on paper, in equations, in careful predictions. But science does not stop at what cannot be seen. It learns to observe indirectly. To detect black holes, astronomers look not at the black hole itself, but at its effects on the space around it. One of the earliest clues came from motion. Stars were observed orbiting empty regions of space. They moved quickly, too quickly to be explained by visible matter alone. Something unseen was holding them in place. In some systems, a star appeared to circle an invisible companion. Its path was precise, regular, predictable. By studying this motion, scientists could calculate mass, and the mass was too great to belong to any known object except a black hole. Another clue came from light, not direct light, but light under stress. Gas falling toward a black hole does not disappear immediately. It accelerates, it heats up, it begins to glow. This glow often appears in X-rays, a form of light invisible to human eyes. Special telescopes in space were built to detect it, quietly scanning the sky, listening for signals beyond visible light. These X-ray sources revealed regions where matter was being compressed and heated to extreme temperatures. Again, the explanation pointed to black holes. In other cases, the universe itself acted as a detector. Light from distant stars was seen to bend. Its path curved as it passed near something massive. This bending of light, known as gravitational lensing, revealed mass without visible form. By mapping these distortions, scientists could infer the presence of hidden objects. Black holes also reveal themselves through timing. Signals from surrounding matter sometimes fluctuate. They pulse. They repeat. These rhythms correspond to orbital motion near extreme gravity. By measuring these patterns, Astronomers estimate spin, mass, and structure. In recent years, a new method emerged, one that does not rely on light at all: gravitational waves. When massive objects accelerate, they disturb space itself. These disturbances travel outward at the speed of light. When two black holes merge, they send ripples through the fabric of space-time. These ripples are incredibly subtle. By the time they reach Earth, they are smaller than the width of an atom. Yet with extreme precision, scientists have learned to detect them. Long instruments, quiet environments, and patient observation make this possible. Each detection confirms not only the existence of black holes, but their behavior: mass, spin, distance. The universe speaks in many languages: light, motion, time, and now vibration. Perhaps the most striking achievement in black hole observation came not from motion nor from X-rays, but from patience. By combining data from observatories across the Earth, scientists created a virtual telescope the size of a planet. This allowed them to capture an image, not of the black hole itself, but of its shadow, a dark region surrounded by glowing matter, a silhouette against the brightness of space. This image did not show detail. It did not show structure inside, but it confirmed something essential. Black holes are real. They exist as predicted. They follow the rules described by theory. And yet, even with this achievement, black holes remain distant, untouchable, unreachable. Our observations are careful, indirect, patient. We do not rush toward conclusions. Instead, we gather signals. We compare models. We listen. Black holes teach us that knowledge does not always come from direct vision. Sometimes it comes from influence, from how things move, from how light bends, from how space trembles. In this quiet accumulation of evidence, human understanding grows. Not suddenly, not dramatically, but steadily, over time. As observation methods improved, black holes began to offer more than confirmation of their existence. They began to offer insight into time, into space, into the structure of reality itself. Near a black hole, time does not behave as we expect. It slows, it stretches, it separates from common experience. This is not measurement, it is measurement. Clocks placed in strong gravity tick more slowly than those far away. This effect has been tested, confirmed, repeated. Near a black hole, this slowing becomes extreme. To an observer at a distance, processes near the black hole appear frozen. Motion fades. Change stalls. Yet locally, nothing unusual is felt. Physics continues normally. Cause still follows effect. This difference reveals something important. Time is not absolute. It depends on gravity. It depends on motion. Black holes exaggerate this truth. They make it visible. In doing so, they turn abstract equations into observable reality. They also challenge intuition. What does it mean for time to slow indefinitely? What does it mean for the future to point inward? Inside a black hole, time and space exchange roles. What was once a direction in space becomes a direction in time. Movement inward is not a choice. It is a progression. This idea is difficult for the human mind. Our experience is built on freedom of motion, on reversibility. Black holes remove reversibility. They enforce direction. This enforcement is not malicious. It is structural. From this, physicists learn that reality is flexible. It bends. It adapts. It responds to mass and energy. Black holes also raise questions about information. If something falls in, what happens to its details, its structure, its history? Classical physics suggests loss. Quantum physics resists that idea. This conflict remains unresolved. It is not an error. It is a frontier. Black holes sit at that frontier. They expose the tension between theories. They force new thinking. Some proposals suggest that information is preserved in subtle correlations. Others suggest that it is transformed. None are yet confirmed. All remain under study. Despite these uncertainties, black holes do not threaten the coherence of the universe. They obey rules. They remain consistent. They do not violate causality outside their boundaries. Their mystery lies not in chaos, but in depth. By studying black holes, humans do not seek danger. They seek limits. Limits of understanding. Limits of description. Limits of prediction. These limits are not barriers. They are guides. They show where new ideas must form, where old assumptions must soften. Black holes teach patience. They do not yield insight quickly. They reveal it slowly, over decades, over generations. Each observation adds context. Each measurement refines understanding. There is no final answer yet, only progress. And in this progress, something subtle emerges. The universe is not rigid. It is responsive. It is dynamic. Time is not a backdrop. It is an actor. Space is not a container. It is participant. Black holes bring these truths into focus. They do not explain everything, but they clarify what matters. They show that reality is not built for simplicity. It is built for consistency. And consistency in the universe is patient, quiet, unhurried. As we continue, this understanding will expand, not inward, but outward, toward how black holes connect to the history of the universe itself. As our understanding deepens, it becomes clear that black holes are not merely objects to be studied. They are boundaries. Boundaries between what can be known and what remains beyond reach. Human knowledge grows through observation, through measurement, through prediction. But every method has limits. Black holes reveal these limits with unusual clarity. Outside a black hole, information can be observed. Signals can be measured. Events can be reconstructed. Beyond a certain point, this is no longer true. The event horizon marks a fundamental divide, not just in space, but in knowledge itself. Once information passes this boundary, it cannot return. No signal escapes. No message travels outward. This does not mean that information ceases to exist. It means that it becomes inaccessible. For science, this distinction is important. There are questions that cannot be answered directly, not because they are forbidden, but because the universe does not allow access. Black holes do not hide their secrets out of hostility. They hide them because of structure. This realization reshapes how humans think about understanding. Knowledge is not unlimited. It is contextual. It depends on perspective. From far away, a black hole appears simple, defined by mass, by spin, by charge. Closer inspection reveals complexity, interactions, subtle effects, long-term influence. Yet even with advanced tools, there remains a region where description fails. This failure is not collapse. It is horizon. In physics, horizons appear in many forms. They mark limits of observation, limits of prediction. Black holes make these horizons tangible. They force scientists to acknowledge uncertainty, to work with probabilities, to accept incomplete answers. This acceptance is not weakness, it is discipline. By respecting limits, science avoids speculation. It remains grounded. Black holes also teach humility. They remind us that the universe is not obligated to reveal itself fully. Understanding unfolds slowly, piece by piece, over centuries. Some questions may never be answered. Others may require entirely new frameworks. Black holes encourage this evolution. They motivate new theories, new mathematics, new ways of thinking. They stand as reminders that discovery is a process, not a destination. In this sense, black holes are teachers, silent ones. They do not explain themselves. They challenge observers to refine their questions. They ask not, "What do you want to know?" but rather, "What can you know?" This shift changes perspective. It replaces certainty with curiosity, final answers with ongoing inquiry. At the edge of a black hole, physics pauses, not in failure, but in transition. Transition toward deeper theories, toward broader understanding. Black holes, therefore, occupy a special place in human thought. They are not symbols of destruction. They are symbols of limits. Limits that define science. Limits that shape philosophy. Limits that guide exploration. In accepting these limits, human understanding becomes more precise, more careful, more honest. The universe does not require that everything be known. It requires only that it be consistent. Black holes embody this consistency. They obey rules faithfully, even when those rules exceed comprehension. And in this obedience, they offer a quiet lesson. That mystery is not failure. It is structure unseen. That uncertainty is not ignorance. It is the boundary of growth. As we pause here, at the edge of what can be understood, we prepare to look outward once more, toward how black holes fit into the long history of the universe itself. To understand black holes fully, it is not enough to know how they form or how they behave. We must also understand where they belong in the long history of the universe. The universe has a history, not a story with intention, but a sequence of change, from simplicity to complexity, from uniformity to structure. Black holes appear at many stages of this history. They are not limited to one era. They are woven through cosmic time. In the early universe, conditions were extreme. Matter was dense. Temperatures were high. As expansion continued, the universe cooled. Structures began to form. The first stars ignited. Massive, short-lived. These early stars left behind remnants. Some became black holes. These first black holes were small by modern standards, yet they mattered. They altered their surroundings. They gathered material. They shaped early structures. Over time, as galaxies assembled, black holes grew with them. They became companions to cosmic evolution. In young galaxies, black holes were often active. They fed frequently. They influenced gas dynamics. As the universe aged, activity slowed. Growth became measured. This slowing is visible today. Modern galaxies are calmer places. Star formation is less intense. Black hole activity is subdued. This transition from chaos to calm marks the aging of the cosmos. Black holes record this aging. Their mass reflects the history of their environment. By studying black holes at different distances, astronomers look back in time. Light from distant galaxies takes billions of years to reach us. In that light, we see younger universes. And in those young universes, we see black holes behaving differently, more active, more influential. This comparison reveals how cosmic conditions change. Black holes become markers, not of location, but of era. They help scientists divide cosmic history into phases: early formation, rapid growth, gradual stabilization. Each phase leaves traces in black hole populations. The largest black holes tell stories of repeated mergers, of abundant gas, of dense environments. Smaller black holes tell quieter stories, of isolation, of limited resources. Together, they form a record written not in words, but in mass and motion. Black holes therefore act as witnesses. They do not remember consciously, but their properties preserve information about the universe's past. Through them, scientists reconstruct events long gone. Galaxies that merged, gas that collapsed, stars that burned out. Without black holes, much of this history would remain hidden. They provide anchors for cosmic timelines. They connect the early universe to the universe we see today. In this sense, black holes are not anomalies. They are participants. They participate in growth, in regulation, in aging. They change as the universe changes. And as the universe continues its slow expansion, black holes continue their quiet existence. Not frozen, not finished, but evolving alongside everything else. Understanding their place in cosmic history helps us understand our own place. We live in a universe that has matured, that has slowed, that has settled. Black holes reflect this maturity. They remind us that time is vast, that change is gradual, that stability is earned over billions of years. As we continue forward, this long perspective will help us explore the future of black holes and the future of the universe itself. As the universe continues to age, its behavior changes. Expansion accelerates. Matter becomes more spread out. Energy thins across vast distances. In this evolving universe, black holes also change. Not suddenly, not dramatically, but gradually. Over billions of years, the environment around black holes becomes quieter. Gas clouds grow rare. Star formation slows. With less material available, black holes feed less often. Their growth slows. Eventually, it nearly stops. In this distant future, most black holes become isolated. They drift quietly within aging galaxies. Some galaxies merge, others separate forever, carried apart by cosmic expansion. As distances increase, communication between regions becomes impossible. The universe grows darker, colder, more silent. In this quiet state, black holes remain. They are among the longest-lasting objects in existence. While stars burn out and galaxies fade, black holes persist. Yet even black holes are not eternal. According to theory, they slowly lose mass through a subtle process. This process is known as Hawking radiation. It does not involve light visible to the eye. It is extraordinarily weak. For stellar black holes, this evaporation would take far longer than the current age of the universe. For supermassive black holes, the timescale is even longer, trillions upon trillions of years. During this slow evaporation, black holes shrink imperceptibly. No explosion occurs, no sudden disappearance. They fade. As mass decreases, temperature increases slightly, yet this increase is minimal, barely detectable. Only near the very end of a black hole's life does evaporation become significant. Even then, the process is gentle, brief, quiet. In this far future, black holes may represent the final, structured objects in the universe. Everything else will have dissolved into thin radiation and scattered particles. The universe will approach a state of uniformity, maximum entropy. In this state, change becomes rare. Events become improbable. Black holes delay this outcome. They store mass and energy for immense durations. They slow the universe's journey toward equilibrium. In this sense, black holes are timekeepers. They extend structure into the far future. Their existence ensures that complexity does not vanish quickly. Eventually, even they will be gone. What remains afterward is uncertain. Physics becomes speculative. The universe may continue expanding forever, or it may approach a quiet, cold stillness. Black holes do not decide this fate. They participate in it. They follow the same laws as everything else. Their long lives offer perspective. They remind us that cosmic change is not measured in moments, but in eons. In studying their future, humans confront time on scales far beyond experience. Years lose meaning. Centuries vanish. Only slow transformation remains. This perspective reshapes how we think about permanence. Nothing lasts forever. Not stars, not galaxies, not even black holes. Yet the manner of their passing is calm, predictable, orderly. The universe does not end in violence. It fades. In this fading, black holes play their final role. They hold structure together until it is no longer possible. Then, they release what remains and pass quietly into history. As we reach this point in the story, the discussion begins to shift. Not toward equations, not toward measurements, but toward meaning. Black holes force us to think differently about time, not as minutes and hours, but as deep, unfolding duration. In everyday life, time feels linear. It moves forward. It accumulates memories. It creates urgency. In the universe, time behaves differently. It stretches. It slows. It bends under gravity. Black holes reveal this more clearly than any other object. Near them, time separates from intuition. Moments extend. Change decelerates. This teaches an important lesson. Time is not a universal rhythm. It is local. It depends on conditions. The stronger the gravity, the slower time flows. This is not philosophy. It is observation. Black holes represent the extreme limit of this effect. They remind us that the universe does not operate on human schedules. Stars take millions of years to live and die. Galaxies take billions. Black holes persist for timescales that surpass imagination. From this perspective, human existence is brief, but not insignificant. We exist in a moment when the universe is structured, when stars shine, when galaxies are visible. Black holes help define this moment. They slow the erosion of structure. They delay uniformity. Without them, the universe would simplify faster. Complexity would fade sooner. In this sense, black holes act as anchors in time. They hold mass. They preserve energy. They extend cosmic processes. Their presence gives the universe a longer story. They also challenge our perception of endings. A black hole is not an ending. It is a transformation. Matter does not vanish. It changes form. It becomes curvature. Energy does not disappear. It disperses slowly. This slow transformation mirrors the universe itself. There are no sudden conclusions, only gradual transitions. Black holes reflect this truth. They embody patience. They do not rush collapse. They do not accelerate decay. They stretch time to its natural limits. In doing so, they invite a different way of thinking, not in terms of urgency, but continuity, not in terms of fear, but scale. The universe is not fragile. It is resilient. It changes slowly. Black holes are proof of this resilience. They survive where other structures fail. They persist where stars fade. And yet, they too will pass. Not violently, not suddenly, but quietly. In this quiet passing, the universe continues. Time moves on, unconcerned, steady. And black holes, in their long existence, serve as reminders that time is not an enemy. It is the medium through which the universe unfolds. As scientific understanding reaches its limits, another form of understanding begins, not measured by instruments, but by reflection. Black holes do more than challenge equations. They challenge perspective. They invite humans to reconsider their place within the universe. For most of history, human existence was centered. The earth felt central. The sky felt designed. The universe felt close. Modern astronomy changed this view. The earth became one planet. The sun became one star. The galaxy became one among billions. Black holes deepen this shift. They represent environments where human intuition fails, where common experience no longer applies. Near a black hole, familiar ideas collapse. Distance loses meaning. Time slows beyond recognition. This is not hostility. It is indifference. The universe does not react to observation. It does not adjust to expectation. Black holes exist without regard for understanding. This realization can feel unsettling, but it can also feel clarifying. Human life is brief when measured against cosmic time. Civilizations rise and fall in what amounts to moments. Yet brief does not mean meaningless. Meaning does not require duration. It requires context. Black holes provide that context. They remind us that permanence is rare, change is constant, transformation is universal. Stars transform into remnants, galaxies transform through mergers, energy transforms through radiation. Nothing remains static. Black holes embody this truth without drama. They do not explode continuously. They do not dominate attention. They persist quietly. In this persistence, they reflect a form of stability different from permanence. Stability through balance, through slow evolution. Human existence mirrors this pattern, not in scale, but in principle. Lives are finite. Moments pass. Experiences accumulate. Meaning emerges not from endless duration, but from structure. Black holes show that structure can exist even in extremes. Even where light cannot escape, order remains. This challenges a common fear, that darkness equals chaos. In reality, darkness can be organized, silent, predictable. Black holes are not voids. They are regions of maximum order under extreme conditions. This reframes how we think about absence. Absence is not nothingness. It is transformation unseen. From this perspective, black holes become symbols, not of destruction, but of continuity. They connect what was to what will be. They store history in mass and motion. They carry the imprint of past stars, past galaxies, past interactions. Human history feels fragile by comparison, but it follows the same rule. Nothing is isolated. Everything participates in a larger process. Black holes do not erase information from the universe's story. They relocate it beyond direct access. This distinction matters. It suggests that reality is deeper than observation, that not seeing does not mean not existing. In this way, black holes challenge a surface-level understanding of truth. Truth is not always visible, not always reachable, but still present. This realization has philosophical weight. It invites humility, not surrender, but respect for complexity. Human knowledge grows, but it grows within limits. Black holes mark those limits clearly. They show where certainty ends and inquiry begins. This is not discouraging. It is grounding. It places human thought within a realistic frame. We are observers inside a vast system, not outside it. Black holes remind us that observation is local, partial, context-dependent. Yet even partial understanding has value. It allows navigation, prediction, wonder. Wonder does not require complete answers. In fact, wonder thrives where answers are incomplete. Black holes preserve wonder in a scientific age. They resist full explanation. They remain open-ended. They ensure that the universe is not reduced to a solved problem. This openness sustains curiosity, and curiosity sustains meaning. As humans study black holes, they are not only learning physics, they are practicing perspective. They are learning to exist without full control, without total clarity. This lesson extends beyond astronomy. It applies to existence itself. Life unfolds without complete certainty, without guaranteed outcomes, yet it unfolds meaningfully. Black holes do not negate meaning. They contextualize it. They show that meaning does not come from dominance, but from participation in a larger whole. In this light, human existence is not diminished by the vastness of the universe. It is defined by it. And as the universe continues its slow, patient evolution, black holes remain silent witnesses to the unfolding of everything. As the universe expands in every direction, human awareness expands inward, not outward, but inward, toward reflection. Black holes do not speak, yet they provoke thought. They do not respond, yet they invite response. When humans contemplate black holes, they are not merely studying distant objects. They are confronting scale. Scale changes perception. It reshapes priorities. It alters what feels important. Against the age of the universe, human life is brief. Against the size of galaxies, human presence is small. This contrast can feel overwhelming, but it does not need to be. Awareness of scale does not diminish experience. It clarifies it. A short life can still be complete. A small place can still be meaningful. Black holes reinforce this idea without intention. They exist on timescales that erase urgency. They persist beyond generations, beyond civilizations. Yet they do nothing quickly. They do nothing suddenly. In their stillness, they suggest a different rhythm. Human life often follows urgency, deadlines, decisions, immediate consequences. The universe does not operate this way. It unfolds slowly, relentlessly, without concern for speed. Black holes embody this cosmic tempo. They are reminders that time does not rush. This perspective invites a shift. Instead of asking, "What must happen now?" we may ask, "What is unfolding?" Instead of seeking control, we may seek alignment. Black holes also reveal the limits of observation. No matter how advanced technology becomes, some regions remain unreachable. Some answers remain incomplete. This is not failure. It is structure. The universe is not designed for full transparency. It contains depth by necessity. Human awareness grows by navigating this depth. Black holes force awareness to coexist with uncertainty. They demonstrate that not knowing does not prevent understanding. It refines it. Knowledge becomes probabilistic, conditional, evolving. Certainty gives way to coherence. This transition mirrors human experience. Life rarely offers certainty. It offers patterns, trends, likely outcomes. Black holes reinforce the value of working within uncertainty rather than resisting it. They also dissolve the illusion that humans stand apart from the universe. Human minds evolved within cosmic laws. Human thought follows the same physical constraints. Awareness itself is a product of the universe. In contemplating black holes, the universe observes itself. This recursion is subtle, not mystical, but factual. Atoms that formed in ancient stars now assemble thoughts about those same stars' remnants. Black holes close this loop. They represent endpoints of stellar life, yet they inspire new beginnings in understanding. They show that endings and beginnings are not opposites. They are phases. Human consciousness mirrors this structure. Memories form. Experiences fade. Understanding evolves. Nothing remains static. Black holes also highlight the difference between significance and centrality. Humans are not central to the universe, but they are significant within it. Significance arises from awareness, not position. Black holes have no awareness, yet they shape awareness indirectly. They alter how humans think about permanence, about fear, about importance. Fear often arises from misunderstanding scale. Black holes seem terrifying when imagined incorrectly, as devourers, as threats. In reality, they are distant, rarely interactive, governed by precise laws. Understanding replaces fear with proportion. This pattern repeats through scientific history. What was once frightening becomes structured. What was once unknown becomes contextual. Black holes follow this pattern. They shift from myth to measurement, from fear to framework. This shift does not remove mystery. It deepens it. Mystery becomes grounded rather than imagined. Grounded mystery is calming. It allows acceptance without surrender. Black holes encourage this acceptance. They show that reality is not obligated to be comforting, but it can be coherent. Coherence is enough. It allows meaning to form without illusion. Human awareness grows strongest when it aligns with reality rather than resisting it. Black holes teach alignment through scale. They invite humans to slow down thought, to widen perspective, to release urgency. In this slowing, understanding becomes deeper. The universe does not ask to be conquered. It asks to be observed. Black holes reward observation with insight. Not instant insight, but accumulated clarity. And as this clarity grows, human awareness finds balance. Not through dominance, but through context. Not through certainty, but through coherence. In this balance, the presence of black holes is no longer unsettling. It becomes grounding. They remind us that existence does not require explanation to be valid. As awareness settles into perspective, a quiet realization emerges. The universe is not loud. It does not rush. It does not demand attention. Even its most extreme structures exist in silence. Black holes, often imagined as violent forces, are in reality among the quietest presences in the cosmos. They do not roar. They do not chase. They wait. Most of the time, nothing happens around them. Stars continue their paths. Galaxies rotate slowly. Space remains calm. This calm challenges expectation. Human imagination often fills the unknown with urgency, with danger, with threat. Black holes dissolve this habit. They show that the unknown is not inherently hostile. It is simply unobserved. Silence does not imply menace. Darkness does not imply chaos. In the universe, silence is the default state. Sound requires matter. Motion requires interaction. Drama requires proximity. Black holes exist far from most things. Their influence extends, but their interaction is rare. This distance matters. Fear often comes from imagining closeness where none exists. Understanding restores distance. It places objects back into their true scale. Black holes are distant. They are sparse. They are governed by precise limits. They do not wander randomly. They do not grow without constraint. Their behavior is predictable within known laws. Predictability brings calm. The universe, when understood correctly, is not threatening. It is indifferent. Indifference is not cruelty. It is neutrality. This neutrality allows stability. Black holes operate within this neutral framework. They obey gravity. They follow conservation. They evolve slowly. Nothing about them suggests urgency. This realization offers something rare: permission to relax. If even the most extreme objects do not rush, why should thought? Why should awareness remain tense? Black holes invite a slower mental pace. They suggest that existence does not require constant reaction. The universe unfolds whether we watch or not. This does not reduce meaning. It frees it. Meaning no longer depends on intervention. It depends on observation. In watching the universe, humans participate without control. Black holes reinforce this mode of participation. They cannot be altered. They cannot be negotiated with. They simply are. This being is not confrontational. It is passive. Accepting this passivity can be calming. Much of human stress comes from resistance to conditions that cannot be changed. Black holes represent conditions beyond change. They exist on scales where intention is irrelevant. Recognizing this allows a release of responsibility for the uncontrollable. One does not need to solve the universe to exist within it. One does not need to penetrate every mystery to find peace. Black holes confirm this truth. They are mysteries that do not ask to be solved. They ask to be acknowledged. Acknowledgement is quieter than explanation. It requires less effort. In this acknowledgement, an unexpected calm appears. The unknown becomes spacious, not threatening, open. Black holes create space not only in physics, but in thought. They create room for unanswered questions to exist without pressure. This room is essential for rest. Rest does not require certainty. It requires safety. Understanding provides safety, not by eliminating mystery, but by framing it accurately. Black holes are framed now, not as devourers, not as enemies, but as distant structures within a consistent universe. Consistency is comforting. A universe with rules allows rest. Black holes follow those rules faithfully. They do not surprise. They do not violate expectation once understood. This reliability extends calm to the observer. As thought slows, the universe feels larger, but less oppressive. Its scale no longer intimidates. It contextualizes. Context removes urgency. Urgency fades. Attention softens. In this softened attention, the mind rests. Black holes remain, unchanged, unconcerned. They do not notice observation. They do not require response. They simply persist in quiet balance. And in that persistence, they offer a lesson without words. That existence does not need to be loud to be profound. That silence is not emptiness. It is stability. That the unknown can be held gently, without fear, without demand. As awareness rests within this understanding, the universe feels less distant, not because it is closer, but because it is calmer. And in this calm, there is space to let thought slow, to let attention soften, and to allow rest to arrive naturally. As the universe continues to expand, its behavior begins to change. Not suddenly, not dramatically, but gradually. Expansion does not only increase distance, it reduces interaction. It separates matter. It thins energy across space. In the early universe, matter was close. Collisions were frequent. Stars formed rapidly. Energy flowed easily. Structures emerged quickly. But as time passes, this density fades. Galaxies drift farther apart. Gas clouds become sparse. Opportunities for star formation decline. The universe enters a slower phase. Stars still exist, but they form less often. They burn more quietly. Massive stars, which once dominated early eras, become rare. Smaller stars persist longer. They shine steadily. They consume fuel slowly. Over billions of years, even these stars begin to fade. The cosmic supply of fuel is not renewed. Hydrogen becomes locked inside remnants. Star formation becomes inefficient. Eventually, it nearly stops. Galaxies that were once bright grow dim. Their spiral arms lose definition. Their cores quiet down. Energy output across the universe declines steadily. This process is not collapse. It is dilution. The universe does not fall inward. It spreads outward. With this spreading, temperature decreases. Radiation stretches. Light loses energy. The cosmic background cools further. Events become rare. Interactions become infrequent. Change slows. This phase is sometimes described as the aging of the universe. Not an ending, but a transition. In this aging universe, structure still exists, but it becomes harder to create. New stars struggle to form. New galaxies do not appear. What remains are remnants, white dwarfs, neutron stars, black holes. These objects no longer produce energy. They store mass. They persist. The universe shifts from creation to maintenance, from growth to endurance. Energy gradients flatten. Temperature differences reduce. The universe approaches equilibrium. This approach takes immense time, trillions of years. During this time, motion continues, but slowly. Galaxies orbit within clusters. Clusters drift apart. Nothing forces acceleration. The universe becomes quiet, not because something breaks, but because everything spreads. In this calm environment, only the most stable structures remain relevant. Objects held together by the strongest forces. Gravity becomes dominant, not because it grows stronger, but because other forces lose opportunity. Electromagnetic interactions require closeness. Nuclear reactions require fuel. Gravity requires only mass. As long as mass exists, gravity persists. This shift elevates the importance of compact objects, dense, durable, long-lived. The universe enters an era where persistence matters more than activity, where survival depends on stability, not production. This prepares the stage for what remains when nearly everything else has faded. Not emptiness, but endurance. In the next phase, these enduring structures will define the universe's character. They will not dominate through action, but through presence. And among them, one class of object will outlast almost all others. Their role does not begin with noise, but with patience. As the universe enters its slower phases, most active processes begin to fade. Stars exhaust their fuel, galaxies lose their brightness. Energy production declines steadily. In this environment, only the most stable structures remain relevant. Black holes belong to this category. They do not depend on fuel. They do not rely on nuclear reactions. They do not require close interactions. They persist through mass alone. As long as mass exists, black holes remain. In aging galaxies, black holes outlive nearly everything around them. Stars burn out, gas disperses, radiation thins. Yet black holes stay. They no longer grow rapidly. Material becomes scarce, accretion slows. Most black holes become dormant, inactive, silent. Dormancy does not mean irrelevance. Even inactive black holes continue to influence their surroundings through gravity. They hold stellar remnants in orbit. They anchor galactic cores. In galaxy clusters, supermassive black holes remain at the centers of mass. As galaxies merge less frequently, black hole mergers also become rare. The universe loses opportunities for dramatic events. What remains is persistence. Black holes represent the most efficient form of long-term mass storage. Matter locked inside a black hole is protected from dispersion. It does not evaporate quickly. It does not decay. This makes black holes important actors in the far future of the universe. They delay the universe's approach to uniformity. While other structures dissolve, black holes maintain contrast. They preserve gravitational wells long after stars are gone. In a universe approaching equilibrium, any remaining structure matters. Black holes provide that structure. Over immense timescales, clusters of remnants continue to orbit black holes. Motion persists, but it is slow. Change continues, but it is subtle. This era is sometimes described as the era of remnants, an era where creation has ended, but existence continues. Black holes dominate this era not through activity, but through endurance. They do not shape the universe by producing energy, but by resisting dissolution. Their influence is conservative. They conserve mass. They conserve structure. In this way, black holes oppose entropy locally, even as the universe as a whole moves toward uniformity. This opposition is temporary, but it is significant. Without black holes, the universe would reach equilibrium sooner. Their presence stretches cosmic timelines. They extend the period during which structure exists. As time progresses further, even black holes are not immune to change. According to current theory, they slowly lose mass through quantum effects. This process is extremely weak. It operates over timescales far beyond stellar lifetimes. For most of cosmic history, this loss is negligible. Black holes remain effectively stable. They become the last major repositories of mass and energy. In a universe with fewer interactions, this concentration matters. Black holes thus define the character of the late universe, not as destroyers, but as survivors. They do not accelerate decay, they delay it. They do not amplify chaos, they preserve order locally. As the universe continues to thin, black holes remain as reference points, markers of where mass once gathered, traces of a more active past. Their existence links the energetic universe to the quiet one that follows. They bridge eras. In the next and final phase, even this endurance will reach its limit. What happens then belongs to the final stage of cosmic evolution. As the universe moves deeper into its late stages, most familiar processes have already ended. Stars no longer form. Galaxies no longer evolve. Energy production has ceased. What remains is not destruction, but simplification. The universe becomes quieter because interactions grow rare. Matter is spread thin. Distances are vast. Only long-lived objects persist. White dwarfs cool slowly. Neutron stars lose activity. Over immense timescales, even these remnants fade. Black holes remain longer than nearly all other structures. They do not require fuel. They do not emit light. They persist through gravity alone. In this late universe, gravity becomes the dominant force. Other forces depend on proximity. Gravity does not. Black holes, therefore, shape what little structure remains. They anchor motion even when motion is rare. Eventually, even black holes begin to change. According to theory, they lose mass through extremely weak radiation. This process is slow. For most of cosmic time, it is negligible. Only in the far future does it become significant. When a black hole disappears, it does so briefly, without prolonged activity. What remains afterward is diffuse radiation spread across expanding space. At this stage, the universe contains no complex structures. Matter has transformed. Energy has dispersed. The universe has not collapsed. It has stabilized into its simplest physical state. This is not an ending. It is completion of physical transformation. As the universe settles into its quiet state, there is nothing left to explain, nothing left to measure, nothing left to resolve. The processes that shaped everything have completed their work. Matter has transformed. Energy has dispersed. Structure has softened into simplicity. The universe continues, not with events, but with presence. There is no urgency now, no direction to follow, no change to anticipate, only continuity. Time no longer marks moments. It stretches without distinction. Space no longer separates what no longer interacts. What remains is not emptiness, but stillness. A stillness governed by order, by consistency, by laws that require no attention. The universe does not end. It rests within its final state. Not silent because something is missing, but silent because nothing is required. This silence is not absence. It is completion. Everything that could unfold has unfolded. Everything that could change has changed. What remains is enough. The universe does not observe itself. It does not reflect. It does not remember. Yet it continues without effort. In this continuation, there is no demand for awareness, no need to follow, no need to hold attention. The universe carries on, whether watched or not. And now there is nothing left to do. No question waiting, no answer required. Only the quiet persistence of existence itself. As this journey ends, it does so gently, without finality, without declaration, simply by slowing and allowing stillness to remain. Good night.